All right, guys, so welcome back. This is our lesson on energy and conservation of energy and some different ways to look at energy situations. In another video, I'll go over work and power, but we'll tie it in a little bit towards the end here of this lesson. So in the beginning of this video, it's talking about the PhET Energy Skate Park Basic Lab. So you should do that first, really. Like that's going to give you some concrete experience of like dealing with energies and looking at how conservation of energy and energy transformation occurs. So I think that's a really good place to start. So you should go ahead and do that simulation maybe before you watch this video. And there's another video that explains what you should do with that simulation. So go try to do this activity first and then come back to this video. If you've already watched that video, then I'll just jump right in and start talking about energy and different forms of energy and how they all fit together. And you should have some experience from that simulation. So energy is defined as a quantity that has the ability, or it's the ability to change or move matter. So if you have that ability to change or move matter, you have energy. Changing and moving matter, changing matter can just like change the form of it, or moving it is more what we focus on here, which is like, displacing it some bit. The unit for energy is a joule, which is equivalent to a Newton meter. If you watch the video on work, Newton meter makes sense. And it is approximately 1 joule of energy. If you had 1 joule of energy, that would be enough energy to lift one apple, like a medium-sized apple, a distance of 1 meter. So if you put it on your table and you lifted it up to a height of 1 meter above your table, then that would be 1 joule of work that you have used to do that. Okay, so there are two main types of energy or groups. The first one is called mechanical energy, and the second one is called non-mechanical energy. So mechanical energy is represented by the letters ME, and it is energy that is easily transferred to move or change matter. So forms of energy like kinetic and potential fall into mechanical energy. The idea there is like that energy easily easily causes motion or easily causes the change in the situation for that object. The other type of energy, non-mechanical energy or NME, is energy that cannot easily be transferred to move or change matter. Heat, sound, light, those are forms of energy that fall into that category. Mostly in this class we focus on heat and sound. So it's sort of like the wasted energy. So this is the energy that does stuff, that causes the change, causes the motion. And then this non-mechanical energy is sort of the, I don't want to say lost because it's not really lost, but it's the energy that's not really useful. It's kind of wasted. All right. So getting into mechanical energy, the first form that you're probably familiar with the best is kinetic energy. So it's energy due to motion. And the equation for it is Ke equals 1/2 mv squared, where K is the kinetic energy, half is just a constant, m is mass, and v is the velocity or speed squared. So the idea here is that like the faster something moves, so if I had an object that was moving, had some mass m, because of that motion, it has kinetic energy. So if you imagine like you're throwing a baseball and it goes and runs into something, it can obviously change or move the matter that it runs into, so it can like break a window or something like that. So if that's my window and the ball is flying into the window, it would change or move that matter because of the energy that it contains in this mass moving at some speed. The idea here is if you increase the mass or you increase the speed, so the velocity gets bigger or the mass gets bigger, then that's going to increase the kinetic energy because they're all directly related. Potential energy, in general, there are two types that we'll talk about, but it's energy of position or configuration. It's stored energy. So it's not being used at that moment. It's like because there's some sort of configuration or position associated with an object as it changes, that energy, that stored energy can convert into other types. A lot of times it converts from potential energy into kinetic energy, and the kinetic energy causes the change. So the first one we're going to talk about is for gravity, and that's called gravitational potential energy. And gravitational potential energy is GPE, and the equation for it is mass times gravity times height. So gravity being the acceleration due to gravity, that's the 9.8 number, 9.8 meters per second squared. You don't have to worry about the negative because, again, the negative just means moving down. And then h is the height above some zero level. So if we had an object like, I don't know, a brick and it was on the surface, then it wouldn't have any gravitational potential energy because its height would be 0. So if this is like height equal to 0, that's the lowest point it's going to get to. So usually we call that lowest point 0. And then if we lift it up, though, as we lift this brick up, the higher it goes, the more energy it has. Because if you think about it, like if you put something down here and you drop the brick on it, that energy that is stored in the brick as is in the air at some height because of its mass and because it's in the Earth's gravitational field, it has energy there. And that energy would convert into and transform into kinetic energy, and that kinetic energy would actually do the work, but or change or move the matter. But the idea is that these three factors, again, impact the amount of energy that's there. So the mass, the bigger the mass, so if you had a bigger brick or a bigger object, the more massive it is, the more energy it's going to have. The acceleration of gravity is kind of fixed, especially since we do our problems on Earth. But if you had some situation where you were on a different planet that had more or less gravity, that would affect the gravitational potential energy. And then that height. So the higher it goes, the more the gravitational potential energy. So they are all directly related. So if you increase any of these factors, M, G, or H, then the GP will go up. The other type of potential energy that we talk about is things like springs or rubber bands or elastic cords, bungee cords. That's called elastic potential energy, or EPE. So elastic potential energy, the equation for it is 1/2 kx squared. K is the spring or force constant, and that describes how stretchy or how difficult it is to stretch or compress the object. So if you had a rubber band and you imagine a rubber band and you stretch it, the more you stretch it, the more energy it has, right? So like if you're trying to shoot a rubber band and make it fly across the room, the more you stretch that rubber band, the more energy it has and the further it can fly. Now, if you tried to stretch a like real thin rubber band, like, I don't know, a hair tie, versus like one of the thicker rubber bands that you might have seen, the thicker one usually has what's called a bigger force constant. So it takes more energy to stretch that to that distance. X is the distance that it's stretched, or the displacement from equilibrium that it's stretched. So it's like how much the position or how much the size has been converted. And for springs, you can compress or stretch things, and they work that way. So 1/2 kx squared is the equation for that. Again, these are all directly related. So if you increase the force constant or spring constant, or you increase the distance stretched or compressed, that's going to increase the elastic potential energy. So those are the main types of mechanical energies that are present and what we will use to solve for those types. Non-mechanical energy is energy that cannot easily change or move matter. So again, heat or sound, I mentioned that before. Light is another one. So if you think about those other energies like kinetic or potential, I think you can come up with various examples that would cause some sort of movement or change in matter. Sound and heat, heat can be, but it's like through a complicated process. You have to have like a steam engine or some sort of engine that's going to work to do work. Sound is not as easy. So like if I just yelled at something, it's not going to fly across the room because I yelled at it. That's not how that works. So this non-mechanical energy, heat and sound, that is often kind of the wasted energy. It comes from, a lot of times in situations, it comes from the work done by friction. So that's this non-mechanical energy. So if you can figure out how much non-mechanical energy is, it's like the work that's done by friction. So again, I told you to go through this simulation, so let's try some questions about it. And it ties in kinetic and potential energy. This is gravitational potential energy and kinetic energy. And then the total energy is just, you sum everything up. So the thermal energy is the non-mechanical. If you put all these together, you get the total. And let's ask some questions. So it says, at which position is the skater according to the energy graph? So if you look at this graph here, and at this moment, we want to figure out what position it's at. So if we look at the energies that are there, it's got the kinetic energy that's green, it's got the blue potential energy. It looks like they're pretty close to about halfway, right? So this is, I don't know, a little over 3,000 joules, and this is like maybe a little over 1,600 or around 1,600 joules. So I would say they're about even. So you would have to think about, okay, what point would they have an even amount of energy? And I think that's C. So it's like C is about halfway down. So if it started at A, had all potential up here, which makes sense. That's the blue part here, and it has no kinetic. And then it's sliding down the ramp to position E. So position E would be at the very bottom of the ramp. So it would have no potential energy anymore because it would be at the bottom, it would be no height, and it would have all kinetic. So this is kind of in between, so that's where I would pick C. If it was more like B or D, you would have to be more than halfway or less than halfway up the ramp. All right, so let's try another one. So we have this energy bar chart where it has mostly kinetic energy, a little bit of potential. They add up to the total. That is one of the things that you should have recognized through that simulation activity. So it's not C because that was where they were half. I would say it's not D or E or A because that's like the extreme points where it would all be gravitational and all be kinetic. So we have more kinetic than potential. So I'm going to say it's further down the ramp here, and that should be D. Another one, what position is skater here at this one? So this one's mostly potential energy and a little bit of kinetic, so I think that's going to be B. We talked about that's the last one that we haven't talked about in those positions. Again, you can represent energies with pie charts. You can represent it with bar charts. It doesn't really matter. All right, so let's try this one. What is the position of 4? So this is 4, and we want to know which of these pie charts that are present makes the most sense. So again, if it's starting here and it's going through and it's at position 4, it's at this position, we got to look at kind of what's going on. So again, at the top, it's going to be all gravitational potential energy. So that would be the blue. So I don't think it's at that position. And then down here at the bottom where it's at the lowest point, that would be all kinetic. So it's not that position. I don't think there's a chart that says all kinetic, but this one's really close, so it's probably not that one. So it's one of these two in the middle, and we have to decide, is it halfway or more than halfway or less than halfway? So if I just draw the kind of line going halfway between, that's the whole distance, then halfway is probably about here, maybe around there. I would say it's a little below halfway, so it's got more kinetic than potential, and I would call that C. So just kind of looking at examples and trying to figure it out. We have another question about this one on the next one. So it says, what would happen if the object is heavier at position 4? So now it's just got heavier. How would the pie chart change? So if we had a pie chart which had the position 4 energy, which we just had on the last one, now we want to know what would happen in the pie chart. So there wouldn't be any changes. The pie chart would get bigger. Pie chart would or potential energy would increase, or the kinetic energy would increase. I don't think the potential and kinetic energies are going to, they might increase in total, but the percentage of them that makes up that pie chart is going to be the same. I think there is going to be a change. The pie chart's going to get bigger. So mass, if you think about this, what kind of energy did it have in the beginning? It had gravitational potential energy, so GPE, and that is based on mgh, right? So we have now made the mass get bigger, so this number gets bigger, which is going to make the gravitational potential energy get bigger. And if that's true, then the whole circle is going to get bigger. So there's going to be a bigger circle now because there's a bigger mass. But when you get to 4, it's still going to be the same kind of breakdown of amount of potential energy and kinetic energy. All right, number 4, or this part, number 4, we're trying to decide if the kinetic energy is getting taller, which way is this moving? So are we moving down the ramp or up the ramp? So if we look at the kinetic energy is getting bigger. If your kinetic energy is getting bigger, you're going faster. So things usually go faster as they move down. So I'm going to say it's that one. You can also look at the potential energy. So the potential energy here, this is the initial potential energy at 4, and this is the next point. So this bar is getting smaller. If that bar gets smaller, that means that the mass isn't changing, the gravity isn't changing, the height is getting smaller. So yeah, it's definitely moving down in that one. Okay, I'm going to skip over some of these, but they're in the handout, so you can go through them as well. So some of these, like this one's all kinetic energy, so I would say it's, it could be moving at a constant if it just stays there. It's just going, I would say, kind of fast because all the energy, but it doesn't really have a scale or anything like that. So again, I'm going to keep going. All right, so I want to talk about this example with you guys. So the in D2L, there's a paper that you should read through and kind of try to understand energy and energy transfer. It's just like a way to look at things. And they use these LOL charts. So I'm going to highlight this and talk through this. So this bar graph is one L. This second bar graph is another L. And the circle in the middle is the O. So it's not really like amusing, funny, or anything like that. It's just talking about the shape of the graphs that are there. So what we're going to do is we're going to look at kind of a situation and make an LOL graph. So the initial point that we're discussing is when the ball is up here in Buffy's hand. That's initial. And then our final position that we're considering is when the water balloon hits Biff, and Biff's down here. So this is the final point. So you can do this for any situation. Like you're just analyzing the energy that's in a situation, in a system at a certain point. And the system is really important. So the system is anything that you are considering to have energy. And then if it's not part of your system, it's outside of your system, and it can add or subtract energy through the process of work. So in the beginning, if you look at this graph, they have 1, 2, 3, 4, 5 bars of gravitational potential energy. We don't really have a number for that. We're just making up, like, I'm just counting spaces, so that's 5. So it's got 5 joules or 5 whatever bars represent of gravitational potential energy. In our system, we have Biff, we have the Earth, and the balloon. So let's just talk about each one of these. So the balloon is important because that's the thing that's like flying through the air. So you can imagine that has some energy as it's moving, because kinetic energy and such. You might not know why you consider the Earth. This is why we consider the Earth. If we're going to talk about gravitational potential energy, you need the acceleration due to gravity, which means that you need the Earth. So the Earth is what causes that 9.8 meters per second squared. So in order to talk about gravitational potential energy, you have to have the Earth. So if you're going to have that as one of your forms of energy, you got to talk about it, and you got to have it in your system. Biff is our villain at the bottom here from Back to the Future, and he's getting hit with a water balloon for some reason. And he is going to have some energy change there too. So we'll talk about him. All right. So in the beginning, that's what we got. And then if you look over here at the end, they've kind of somehow measured the different types of energy, and let's try to identify where these are coming from. So there's kinetic energy. When the balloon is hitting Biff, it's moving. So I would say that's the energy in the balloon. That looks like 2. Gravitational potential energy, there's still gravitational potential energy here because the balloon is not all the way down at the lowest level. So this is like HF here versus the initial height that it had, which was up in Buffy's hand there. So that would be like HI. So, but if you compare those bars, it went from 5 to 3. So it definitely went down. So that's okay. And then we have this other stuff here, this non-mechanical energy. That's our heat and sound. That's what I would imagine happens when the balloon runs into Biff. There's going to be some heat and sound generated. And that is 2 bars. So if you look at this, this is 5. If you add up 2 and 3 and 2, that is 7. So that seems to violate our total energy in the beginning and total energy final being the same. And that's because we have an outside entity or an outside object adding or subtracting energy through the process of work. So it says Buffy is outside, and if you count how many bars Buffy has 2. So Buffy is putting 2 in. That's why the arrow's going in. So this is going to be like positive work. If the arrow happened to be going out, that'd be negative work. That's fine too. But if you look at it, all we're going to do is we're going to write down these things. So it's just total energy initial, or the total energy at one point, plus whatever work is done, either going in or out. So it's like the external or the net work. Those are your external bodies that add or subtract energy. That should equal the total energy final. And again, if you read through this, I think it makes sense in that sheet in D2L, but I'm just kind of hitting the highlights here. So again, our total energy in the beginning is all gravitational. So that's that. Our work is from Buffy. We have our kinetic energy, our gravitational potential energy, and then the non-mechanical energy. Again, and now if we do it, we have 5 plus 2 would equal 2 plus 3 plus 2. So it's kind of the one of the ways that I've heard this expressed as, it's just like the bars in the beginning, however many bars you have in the beginning, plus whatever bars go in or out should equal the bars that you have at the end. So in this case, Buffy added energy. How did Buffy add energy? Let's think about that for a second. Buffy threw the balloon. So like she took energy that was inside of her and stored inside of her through like chemical energy, and she pushed on the balloon and gave it kinetic energy. So she added energy to the system, and then after that you could see the system and what happened at the end. So so this is how conservation of energy works. This equation right there that I just put a box around, that is essentially the conservation of energy equation for any situation. So you just look at all the different energies that you have before, all the different energies that you have after, and then if you had any processes that added or subtracted energy along the way. You don't always have to, like, again, and the amount of energy, what you have here, is dictated by what is in your system. If we didn't put, say, BIF in our system, some of the energy would escape through heat and sound. Or if we didn't include the Earth in our system, then we wouldn't have gravitational potential energy in the beginning. So it's really like what you decide to put in here determines what energy considerations you make. So let's try this one here, and we're going to work through this one together. And then we'll get into some other ideas about, doing a little bit more numeric of a solution and doing some equation work. So it says a block is pushed at a constant speed. That's usually important. Up a ramp from point A to point B. The direction of the force on the block by the hand is horizontal. So the hand is actually like pushing across like this, but as a result, it still moves from like it's sliding up the ramp. It says there is friction between the block and the ramp. And then the distance between points A and B is a meter. They give you some information you don't really need. It says make an LOL diagram for the motion from point A to point B. So let's consider the things that we want to be part of our system. So I think the block is a good thing because that's the thing that's moving. So we want to write the block in our system. I'm going to say that the Earth is probably important because if you look at it, it's going up the ramp. So I would say that there's probably gravitational potential energy involved from point A to point B. There's some like height difference. So so that's like the height of B above A, if we think about it that way. So I would say the Earth. And then we can include the ramp itself because there's some friction there, and friction, the work done by friction, as I said earlier, is the thing that's going to do non-mechanical energy. So let's say at point A, it's just moving. So at point A, it's just moving. It's got kinetic energy. So I'm going to make a bar for kinetic energy. Again, I don't know amount. I'm just going to say it's 2. So we're just going to make up a number. At this point A, it's at the lowest point. So I'm going to say there's no gravitational potential energy. There is no elastic potential energy because there's no spring or stretchy object. And at point A, it hasn't really started the sliding part and having the friction. So I would say that's non-mechanical energy. At the end, it says it moves at a constant speed from A to B. So if it has a constant speed and the block isn't changing size, I would say that this kinetic energy hasn't changed. So that's going to be 2 still because it's constant speed. It has gained gravitational potential energy. So if I put in, I don't know, we'll just make it 1. 1 block of gravitational potential energy, it is above where it started, so it gained some of that. Still no spring. And there was friction as well, so let's put in some friction stuff. So that would be the non-mechanical energy. So if I look at this, 2 is not equal to 4. So I have like some difference in that. So to go from the total energy in the beginning, the initial, or at point A, you can use A and B, it doesn't matter. To get to B, there'd have to be some change. So there has to be something giving this system energy, and we're going to have an arrow going in. And that arrow going in is a work because the hand is transferring energy. So it's the work by the hand. And if we just think about this kind of logically, if we had 2 to start and we ended up with 4, the hand had to put in 2. So I'll make 2 bars there for the hand. So that's going to be 2. And again, this is where you come up with kind of your relationship. So the total energy at point A plus whatever work is external, the net work, the energy that goes in or out, that's the work. And then that equals the total energy at B. So if I was writing this into an expression, it would be kinetic energy at A plus the work done by the hand should equal all the energies that I have up here. So I have kinetic energy at B plus the gravitational potential energy and the non-mechanical energy. Now, I just made up numbers again. So I just said, oh, this kinetic energy was 2 and then 1 and 1 for the other energies. In the problems that have numbers, you'll be able to plug into those kinetic energy, gravitational potential energy, elastic potential energy, the work equation. You'll be able to plug into those and get these values. I just made up some numbers to make it easier to kind of visualize. So if that's 2 and we had 2 going in, that should equal 2 plus the one of gravitational, and the one of non-mechanical. So, so this again, it balances out. 4 equals 4. So energy was conserved. Conservation of energy works. The work energy theorem works. All those things work. So, so that's just an example of that. So again, the work energy theorem is basically conservation of energy, just in a different format. So the net work done is equal to the change in energy. If we just look at this equation that we just had, we want the net work on one side and we want everything else on the other. So if I subtract that from over there, we would get like the net work done is equal to the total energy at the ending point. So change in energy would be final minus initial. So that is this exact same expression. So this is really just another way to say conservation of energy. Sorry. My phone just had some emergency thing go off. Sorry for that. That startled me too. So that is just conservation of energy, just rearranged a slightly different way. We had it over here where we added the total energy in the beginning plus the work net to get the final. Over here, it's just like, oh, the work net is equal to the difference in those energies beginning and final. So that's fine too. So again, if the energy of the system increases, if we get a positive change in energy, and we can write T or E, that's fine, then we had positive work. If it's a negative change of energy, if the final energy is less than the initial energy, then that would be negative work being done. Okay. So so let's try this problem. This is, I think, the last thing that we're going to do on this video. It says a 4-kilogram bowling ball rolls at 2.5 meters per second. It slows to 1.5 meters per second as it moves 10 meters due to friction. All right. So again, we could do an LOL chart. I'm going to do a really quick one here. And I'm just going to put the ball as the only thing that we care about. So we're not going to deal with the floor. The floor is outside of our system. So let's try to think about this. So in the beginning, this ball is moving at 2.5 meters per second. So what kind of energy it has? I would say it had kinetic energy. So we'll say this is kinetic energy initial. And then at the end, it's moving, but it's moving slower. So it's going to have a smaller bar, and that's going to be kinetic energy final. These are not the same amount of numbers. There aren't any other types of energies, no gravitational or elastic or non-mechanical, because the floor is outside of our system. It's not going to be non-mechanical energy. We're like going to take energy away. So like if this amount, whatever this amount is bigger than that, so like in order to make it get smaller, we have to lose energy. So the arrow is going the other way, and that's going to be the work done by the floor or the work done by friction. All right, so we have kind of the concepts here. We're going to do the problem. Part A says, what's the initial kinetic energy of the ball? So KEI would be equal to 1/2 mv squared. And it's going to be the initial velocity. So if we do this, it'd be 1/2, 4, and then it's 2.5 squared. If you do that in your calculator, you'll get 12.5. And that's joules, because energy is measured in joules. For part B, B wants to know what's the final kinetic energy. So we're just doing the individual kinetic energy. So we're figuring out what these numbers are in these boxes. So that one's 12.5. This one turns out to be 4.5 when you do it. It's 1/2. M is still the mass, and V final squared this time. So it's 1/2 and 4 and then 1.5 instead of 2.5. That's the only thing that's changed in this expression. It's slowed down. And like I said, if you do that, that's 4.5. So it went from 12.5 to 4.5. We're going to look at what is the change in kinetic energy. Right. So our change in kinetic energy is going to be the final, which is 4.5, minus the initial, which was 12.5. And there that's going to be equal to -8. So -8 joules is what happens. It loses 8 joules. So this is -8. So if I started out with 12.5 and I lost 8, I end up with 4.5. That is the idea. So again, it's just, you know, the energy in the beginning, the total energy initial, plus the work the net work should get you the total energy final. And for the last part here, part D, it says, what is the network done? And we should know this already because the network is equal to the change in energy. In this form, it just happens to be kinetic. So it is that -8. Like that's what it is. If we take that over there, it's the same thing that we just did here, 4.5 minus 12.5. That's going to get us -8. So hopefully that is making sense. You're going to have to examine different situations and talk about kind of the energies that are present and do that conceptually at different points and thinking about different types of energy. And then you're going to have to do a couple of problems where you're figuring out numerically what the energies are, kind of like this one. So hopefully that was helpful for you guys in understanding that. I'm going to stop here and have a good day.